In this video, I'm going to give you a quick recap of the information that you'll need to complete this molecular modeling experiment. We're going to review some details, especially about hybridization and molecule polarity, to help you complete the experiment in lab. So this experiment is geared towards helping you understand VSEPR theory, which helps you think about the shape of a molecule based on its groups and how many groups are on the central atom. So we're always thinking about our central atom and the groups around it. Groups can count as a lone pair, a single bond, a double bond, a triple bond, and all of those actually count equally when we're thinking about electron groups in our molecule. So based on the number of electron groups, that tells us the electron geometry. And when we factor in how many lone pairs we have, that tells us about possible molecular geometries. So when we have two electron groups, we only have a linear electron geometry, and linear is actually as far apart as atoms or lone pairs can get from each other, so the molecular geometry also has to be linear when you have two electron groups on your central atom. When you have three electron groups, the furthest apart your atoms can be is a trigonal planar arrangement. In this arrangement, the molecular geometry can also be trigonal planar, and if you have a lone pair, you can also have a bent geometry. The last electron geometry we'll discuss is 4 electron groups. That is a tetrahedral arrangement. So when you're thinking about your atoms or molecule in 3 dimensions, you'll recognize that you'll be able to kind of spread your atoms apart in 3 dimensions, and that's why it's tetrahedral and not square planar. When you have a tetrahedral electron geometry, the molecular geometries are tetrahedral, or if one of them is a lone pair, you can have trigonal pyramidal or trigonal pyramid. And if 2 are lone pairs, then you can have a bent molecular geometry. The electron geometries also tell you about bond angles and hybridization. So let's write down our 3 electron geometries that we discussed. So we use valence bond theory to help us think about hybridization, because otherwise we don't have always a clear picture of what's happening with the bonding. And with a linear electron geometry, we can mix the s and p orbital on our central atom to get an sp hybrid orbitals with a bond angle of 180 degrees. If we mix an s with 2p orbitals, we end up with an sp2 hybrid orbital and a bond angle of 120, and that's what we see when we have a trigonal planar electron geometry. Since we know a p orbital has 3 different orientations, if we use up all 3 of them and get sp3, the bond angle becomes 109.5, and it's a tetrahedral geometry. So that's how we think about hybridization, is generally the electron geometry is going to match the hybridization. The last topic we'll cover in this experiment is molecular polarity. So, is our molecule polar? Well, we know that a polar bond is formed when we have different electronegativity, and we can use Funkel-Brich, which a lot of us teach. If you haven't heard this already, it's fluorine, oxygen, nitrogen, chlorine, bromine, iodine, sulfur, carbon, hydrogen. These are the most electronegative atoms on the periodic table in order. So F is the most electronegative, hydrogen is the least electronegative, and all of these are more electronegative than every other element on the periodic table. So when you're deciding if your molecule is polar, you first have to decide, does it contain polar bonds? If the answer is no, and your elements have the same electronegativity or very similar, then it's going to be a nonpolar molecule. So a good example of that would be CH4. So when we draw this molecule, carbon and hydrogen have pretty much the same electronegativity, and so we wouldn't even draw a polarity arrow because their electronegativities are very similar, and all of the H's, we would not have a dipole moment and the molecule wouldn't be polar. What if our molecule contains polar bonds? So an example of that would be CO2. So if we draw that, we have carbon in the middle surrounded by oxygen atoms. We know that oxygen is more polar than carbon, so we have to check our arrangement. Well, this arrangement is linear, so do the dipoles cancel? In this case, yes, the dipoles do cancel. And so since we answered yes to our question, it is a nonpolar molecule. So an example of this would be CO2. What if we have polar bonds and we check our arrangement, but the dipoles don't cancel? So let's look, for example, at NH3. So in NH3, we have this trigonal pyramidal arrangement of our atoms. We know that nitrogen is more electronegative than hydrogen, but do the dipoles cancel? No, because there's no arrow that's also pointing down. And so the dipoles don't cancel, and our arrows add to overall up, pointing at our nitrogen atom. So the net dipole is here, and the molecule is polar. So an example of this would be NH3. So you can follow this flow chart when you're doing your experiment. It will really help to make the models and see, because the arrangement or the shape of the molecule plays a pretty big role. Oops, meant to highlight that, not cross it off. The arrangement plays a really big role in understanding whether or not the molecule is polar.